All right. Good morning, everyone. We are recording now, finally. So today's lecture will be a bit shorter due to the technical issues we have faced. Um, are there any questions or concerns regarding anything we've discussed so far? Right. So we talked about the paths and cuts, ST paths and ST cuts in particular, right? And I I suggested working out two try it yourself problems. One of them I discussed in the lecture is to find a NP certificate for the shortest path problem, the decision problem, right? So you're given a graph and an ST path between these two vertices, and you want to decide whether this is the shortest path. And here we are referring to the cardinality version. So by shortest, we just mean a path with as few edges as possible, right? So, can you somehow convince your friend that a particular ST path is indeed a shortest path? So, that's one thing I want to discuss today, if time permits. And there's another thing I also want to discuss. So, let's see. So, let's consider if we can find an NP certificate for the decision problem in the cardinality case, right? But apart from that, I also want to talk about the other try it yourself problem that I gave on Piazza, which is to formulate an integer linear program for the shortest path problem. Okay, so let's start with one. So what is the shortest path problem again? So here we are looking at the cost version, but in some sense, what really matters is the constraints, and the objective function is generally quite a standard thing. The constraints are typically a bit more difficult to figure out. So the problem is you're given a graph G with distinct specified vertices, right? So these are two fixed vertices, and you have a cost function or a distance function, whatever you like, um, which gives a cost to each edge. And this we are going to assume is non-negative. This assumption we did not make in the perfect matchings case, but here this assumption is going to be important. Okay, and it also makes sense. Generally, distances are non-negative. So let's just consider this particular case. Um, and the goal is to find, we intend to find a shortest ST path. Shortest meaning of minimum cost. Right? And the cost of a path is the cost of all the edges in the path. I should mention that sometimes I write CE instead of C parenthesis E, but I mean the same thing by that. Okay. Okay, so can we write down an integer linear program for this problem? Which basically means we need to figure out what the variables are going to be and what our constraints are. And generally the easy part is the objective function. Okay. So let's do this. So what should our variables be? You might want to recall the minimum cost perfect matching problem, where we had to find a perfect matching of minimum cost. Right? Here we want to find a shortest path, a shortest ST path. So what do you think should be our variables? What is it that we need to choose?
So it should be the same as sigma CE where C is our
Right. So
cost and
you're
C is in the path or not.
right. So in particular, you're saying that you want XE. So may I assume that you want a variable for each edge?
Yes.
Right. Okay, great. Good. So that's exactly what we want. So let's put a variable for each edge. And I assume you want this variable to be 0 or 1, depending on whether the edge is in your path or not. Is that right?
Yes, sir. It's an indicator
Great.
random variable.
Indicator variable. So let's call it an indicator variable. It's not quite a random variable, but yeah, it's an indicator variable, right? So x equal to 1 means E is in our path. This is sort of the idea we have in mind. Okay? All right. Okay, so that's the variables. Now, okay, so the objective function is quite clear. I'll start writing the ILP on the right side. So we want to minimize the summation of CEXE over all the edges of the graph, right? Okay, and we need to figure out the constraints. So clearly, because this is an indicator variable, we want it to be 0 or 1. Right? So let me just put this down here first. XE is 0 or 1. Let's focus on the more important parts. So what should we choose next? What should our other constraint be, right?
So like the number of edges incident on S and T should be 1, and
Okay.
for every other vertex it should be either 0 or 2.
Okay, let's try that. So supposing one possibility is for S and T, you are saying that the number of edges should be exactly 1, right? Okay. And for every other vertex, you want it to be exactly 2. Is that right?
0 or 2.
0 or 2. For any other vertex V, we want it to be 0 or 2. So summation XE, E belongs to partial V, is either 0 or 2. Right. And for S and T, you want the summation to be
Exactly 1.
exactly 1. Great. And also the same for T. All right. So does this actually capture the property completely? Um, yeah. So your two vertices of degree 1 are exactly the vertices S and T. And the right, for every other vertex, you have 0 or 2. So which means if you look at the graph formed by these edges, it will exactly be a path between S and T. Right. Okay. Fair enough. So this actually does capture the problem completely. I hadn't thought of it myself. This does capture the problem completely. There is one issue though. Remember, what we want to do is we want to get an ILP and then we want to relax it to get a linear program, right? And okay, so that's our intent. We want to get to a linear program by relaxing our ILP. There is one problem here. These constraints are actually not allowed either in an ILP or in an LP, right? What is an ILP? It's simply a linear program where you require certain variables to be integers, right? So how would I relax this to get a linear program? This is a bit too tight because what will happen is we won't be able to use the theory of linear programming to actually make progress on the problem. So what we want to do is we want to get a linear program with just some integrality constraints. And the integrality constraints are basically taken care of here. In fact, we will actually relax this and make this at least 0, and we will make all of them to be integers, like we did in our minimum cost perfect matching problem. The problem is these constraints. These constraints are not actually allowed in an ILP, right? Because this is saying something more than just restricting the variables to be integers, right? So this way of writing constraints does capture the ST path problem exactly. The issue is that it's not really an integer linear program, right? So what we want to do is we want to write a bunch of linear constraints, and then we just want to have integrality constraints for certain variables. And when we actually want to solve the problem, we will drop the integrality constraints. We will look at the linear program, and then we will use the theory of linear programming to solve this problem. Right? So although this is correct, it's not an ILP. In particular, the relaxation is not a linear program. Does that make sense?
Yes.
Yeah. Okay. So let's try to come up with linear constraints instead of constraints that look like basically like integrality constraints acting on a bunch of variables, right? Okay. Good. So all right. So let me for now erase this. But this is actually a complete characterization of the problem. In fact, it's a exact translation from graph theory to this sort of vector way of looking at it, right? Okay. So then what should we do? What should our constraints be? So basically we want linear constraints on the variables. Okay, so let's consider an observation we looked at yesterday. We noted that every ST path must meet every ST cut. So that is an observation I would like you to use. Right? So what would this translate to? For every ST cut, we want to make sure that at least one of the edges is chosen in our ST path. Right? So which means if this is my ST cut, S is here, T is here, this is a set Z and this is a set Z bar. It's a bipartition of the vertex set. I want to make sure that at least one of the edges in this cut is chosen in our path. Right? So that just means that the sum of the variables corresponding to these edges is at least 1. Right? So we can include that constraint. So for each partial z st cut, we want that the sum of all the edges is at least 1. Does that make sense?
So like one doubt, this
Yeah.
for all ST cuts, right? I mean, don't you have exponential number of ST cuts?
That's right. Is there an exponential number of them? Right, because for the vertex S, you can now choose as many other vertices. Right. Yeah, there is an exponential number of these constraints. That is correct. Right. Turns out it's not going to really be a problem when it comes to designing an algorithm. So we won't write down the whole description. I mean, we can write it down in this compact way, but we won't actually need to list down every single constraint. We will still be able to use the theory of linear programming to solve the combinatorial optimization problem. It just requires some tricks. Does that make sense?
Yeah. Yes.
In particular, observe that if I just put these constraints, so let's put this constraint down here. If I just consider these constraints, is this feasible? Supposing you look at this ILP at this point, can you find a solution to this ILP? Let us assume that the graph is connected, or in particular that S and T are in the same component. In that case, can you find a solution to this ILP? I don't want an optimal solution. I just want any solution.
I mean, if there exists an ST path, we'll always have.
Right. In particular, you can choose all the edges, right?
Yeah,
If you choose all the edges of the graph,
correct.
if S and T are in a same component, or if you assume that the graph is connected, just for the sake of simplicity, clearly all your constraints are already satisfied. Because in every ST cut, you would have chosen at least one edge, right? And all the other constraints are satisfied. So, all right, so does this actually capture our problem, or do we need more constraints? If we just look at these constraints, so we have a constraint for every cut, every ST cut, and we have the non-negativity constraint, and we have the integrality constraint. Does this actually capture our problem? Let me give them a name. These are the cut constraints. These are the non-negativity. And integrality. So let me ask you this: if you take an ST path in your graph, will it actually satisfy all the constraints? If you take an ST path P, and for all the edges in the path, you put the XC variable to be 1, and for all the other edges of the graph, you put XC to be 0. Will this be a solution to your integer linear program that we have written down?
It should be.
It should be, right? Everything is non-negative because everything is 0 or 1. All of them are integers. You just need to look at every ST cut. And this observation is telling you that every ST path meets every ST cut. So because you have an ST path, for all ST cuts, it will use at least one edge, and therefore the cut constraints will also be met. Okay? So this implies that each ST path corresponds to a solution to this integer linear program. Okay, that is some good news. But now let's ask the converse question. If you take a solution to this integer linear program, does it correspond to an ST path? Or are there more solutions to this integer linear program than the number of ST paths in the graph? Right? So the question is, does every solution to the ILP that we have written above correspond to an ST path in the graph G? I'm not looking at optimal solutions. I'm looking at all solutions. I'm just looking at the constraints. I don't care about the objective function.
But, just because an edge is part of the cut as well as the path, we cannot create the entire path from these edges, right?
Okay, so I'm still trying to understand. So you mean that a solution may not contain a path, or it could be a path plus other things?
Yeah, I'm saying it may not contain uh, create the entire path between S and T.
Right.
Okay, I'm not clear. I need to think
Okay,
again.
that's fine. That's fine. Okay. So for the time being, you can think of a 0, 1 solution. So don't worry about bigger integers. If you take a 0, 1 solution to this problem, right? Let's make a quick example. So I have a few examples here. Right. It's a slightly big example. Okay. So let's say this is S and this is T, and I've got V1, V2, V3, V4, V5, V6, V8, V7, and that's it. Okay. If you consider this graph and you write down all of these constraints, there is exponentially many of them, but that's fine for now, right? It is still a finite number, which is one of the conditions we need for a linear program or an integer linear program. And now let's say you take any solution to your integer linear program for this graph. Will that correspond to an ST path? Or can you say something along those lines? So let's say we choose an ST path Let's say we choose some edges like this. And definitely this gives you a feasible solution. You put ones for all these edges, these are your one variables, and all the other edges correspond to zeros. Right? And then as we observed, this has to be a feasible solution to your integer linear program. Right? It is a 0-1 solution, and every ST cut will have at least one edge because of this observation. But now you can add more edges to this, right? If you add more edges to your solution, it's still going to be a solution to the integer linear program. So I could now add more edges to this, right? Because I'm adding edges, all of the constraints will still be satisfied. And this solution, this is clearly not an ST path. This is more than an ST path. Right? It contains an ST path, but it has extra edges that can be thrown away. And that is what we can prove. What we can prove is that every solution to the integer linear program, it will contain an ST path, but it might contain more edges. Okay, turns out this is not going to be a problem for us because our interest in finding a shortest path, and because our costs are non-negative, the optimal solutions in some sense, they will correspond to ST paths except for zero cost edges. I'll come to that later, right? Okay, so the point I want to make is that the answer to this is no. What we can prove is that each solution to our integer linear program contains an ST path. Right? In particular, if you look at the edges which have a non-zero number, I mean they could also have two, but it doesn't matter. But if you see an edge which has the XC is equal to 2, it just doesn't mean anything, right? You can just take it to be equal to 1, and it will still be a solution to your integer linear program. Right? So if you look at any solution and you look at the non-zero values, if you look at the edges corresponding to the non-zero values, they will contain an ST path, but they might contain more edges. But that is not going to be a problem for us. Okay, so that's a proposition I want to prove. So in particular, the graph theory way of looking at it is if you consider let G be a graph and S and T be distinct vertices, and now consider any set of edges that meets every ST cut. Let F be a subset of the edges that meets every ST cut. Okay, so means non-empty intersection. Then I claim that if you look at the graph formed by these edges F, so what does this mean? We are looking at the graph whose vertex set is all the vertices of the graph and only these edges. Okay. Then I claim that this contains an ST path. observe that this condition here is the same as saying that this constraint holds, right? For every ST cut, you are choosing at least one edge. Okay? So I would like to prove this statement also as an example of writing a rigorous proof, which you will be expected to even in your assignment 1, right? So it might be good to just prove this result and then move on beyond this discussion, right? So is it clear why we are proving this? I just want to convince you that if you take any solution to this integer linear program, it doesn't correspond to an ST path. It may not correspond to an ST path, but it does contain an ST path. Okay? So it's not an exact formulation like we had in the case of perfect matchings. In the case of perfect matchings, the solutions to the integer linear program and the perfect matchings of the graph, they were an exact one-to-one correspondence. But here, that's not going to be the case. Are there any questions or concerns at this point? Does everybody see why we are proving this proposition? Okay, so how do we prove this? How shall we proceed? I'll give you a hint. Let's start by contradiction. Supposing there is no ST path. Let's start at the vertex S, and let's assume that there is no ST path. What we want to do is, if there is no ST path, we want to be able to find a cut such that the set F does not contain any edges from that cut. Assume that the graph formed by these edges does not have any ST path. Okay? And what we want to do is we want to find a partition of the vertices so that S is on the left side, T is on the right side, and we want to conclude that no edges from this cut belong to the set F. Right? That would contradict our assumption, which is that the set F meets every ST cut.
So if they don't have an ST path, then we can say S and T don't belong to the same component. So we can take
right. Okay. Go ahead.
So one set can be the component of S, and all the remaining vertices can be the other set, and there won't be any tracking edges because we know that S and T don't belong to the same one.
Exactly. That's a complete proof, right? So if you assume that this graph does not have any ST path, what does that mean? By the definition of connected graph, right? It means that S and T in particular are not in the same component, right? If they're in the same component, then there would be a path between them, right? That's the definition of a component. So this implies that S belongs to some component H in the graph formed by these edges, right? And in particular, the vertices of H are a proper subset of the vertices of G, right? So S belongs to some component. So that is going to be our vertex set on the left side. Right? And T does not belong to this component. Right? In particular, T belongs to Z bar. Let Z be the vertex set of this component. Right? So T is on the other side. And now look at the cut corresponding to this component. Right? So consider partial of Z. Note that your set of edges F cannot contain any edge in this cut, because if any edge from your set was in this cut, then that vertex would also be part of the same component, right? Since H is a component in this graph, the intersection of F and partial Z is empty. Right? And that in particular implies that we have a contradiction, because we assumed that for every ST cut, the set F intersects that ST cut. And here we have an ST cut where the intersection is empty. Right? Okay. So which means that if you take any solution to this integer linear program, because the set of edges, they meet every ST cut, it has to contain an ST path. The problem is it may contain more edges apart from the ST path. Okay, but that's not going to be a big issue for us, because we are trying to minimize the sum of the edges, and every edge has non-negative cost. So if you think about it, they are going to basically be the ST paths plus extra edges whose cost is 0. But those we can just ignore. If we find a solution, if we find an optimal solution, we just need to find an ST path in that solution, and all the other edges are going to be 0 cost edges. Right? Or you can just assume in the problem that you don't have 0 cost edges. But generally, you don't make that kind of assumption. It's much more natural to make a non-negativity assumption. So our ILP has more solutions than just the ST paths. Okay? But in some sense, and we'll make this more precise, the optimal solutions will correspond to shortest ST paths plus any edges of 0 cost. Let me just say that. Right? But 0 cost edges are harmless, so let's not worry too much about them. Okay, so one thing I would like you all to try as an example is to find the shortest paths in this example. I'm going to put cost on all the edges. So let's see. Okay, so I'll just put some cost on the edges, and you can try finding the shortest ST paths here, and we'll continue this discussion on Monday. So yeah, because of the time lost, I don't think we are on track, but it's okay. We'll start module 2 on Wednesday. Right, so then we'll switch our focus entirely to linear programs. Okay, so I think I've put cost on all the edges here. If I've missed any edge, please tell me. Okay, so anyways, it's just a toy example. So you can, just by inspection, find the shortest SP paths and maybe see how these correspond to solutions of your integer linear program. Okay. And we didn't get to the second question, but we will get to it on Monday. Okay. So we have an integer linear program for the shortest path problem, and we are going to consider more properties of the shortest of this integer linear program. We will consider the LP relaxation, and on your assignment, you will be generalizing this NP certificate to the case when you have cost on the edges. But we still have to discuss this NP certificate. So let's take that up on Monday. Okay, thanks. Feel free to leave the meeting, but I'm here for another 10 minutes if there are any questions or concerns.
Sir, I wanted to ask about the G of F that you were
Yes.
that you just showed. So will that be
Yes.
will that be a tree? Like, will it have cycles or will it not have cycles?
Right, right. So, I mean, here, you mean in this proposition, it could basically be all the edges.
Exactly. That was what I was thinking. It could be all the edges. So
It could be
it
all
can
the
have
edges. It
cycles.
doesn't have to be tree anything.
Okay, okay, okay.
Exactly, right. In particular, in particular, the solutions to our integer linear program need not be trees or anything. They could just be all the edges of the graph.
Okay, sir. I will think about that.
Right?
I was just confused about how G of F will look because it's a bit hard to imagine right now.
Right, it is just an ST path plus any number of edges you like. So the main point is that it has to contain an ST path.
Okay, so at least one ST path.
Exactly. It will contain an ST path. On top of that, it could have anything else you like. But the key point in our discussion is that the optimal solutions are actually going to be shortest paths. So you assume that all the edges have positive cost for the time being. Then the optimal solutions will not contain any extra edges, because if you already have an ST path, by adding more edges, you are increasing the cost of your solution.
Yes, yes. I got
Do you
this.
agree? So that
Ah,
is the
yes.
key point, that the optimal
Hmm.
solutions will be preserved in some sense.
Hmm.
Yeah.
Yes. Thank you very much. I got that.
Okay. Okay. Thanks. Any other questions or concerns? Madhav, are you still here? Okay, I'm going to remove you from the call. Maybe I'll stop recording first.